Right. Uh, Thank you, Scott. Can you hear me okay?
Yes, fine.
Right. What I'm actually going to present in about 10 minutes is actually what I've been working on with buildingSMART International for the last 10 years, which is getting georeferencing tins, alignments and strings into IFC 4x3. So it's going to be very fast, but just give you an idea of the breadth and what's now available. The problems with IFC 2x3 was it uses a local engineering coordinate system. Basically, that's a 0, 0 in there, and the Earth is flat. So it's called a topocentric coordinate system. And there wasn't anything there for alignments, tins, pavements, and so on. So it was really what I'd call vertical BIM. You have your problems there where you got Australian project, 155 kilometres, where you want a coordinate system that works for the whole project because you work on this in different places. So a local origin somewhere at 0, 0 just does not work. The other horror, which you can see straight away, is if you go out at a height, you've got the curvature of the Earth. So the heights are going to be different. So you've got to allow for that sort of thing with the curvature of the Earth as well. So basically, we need a world coordinate system. And that's what we use as longitude and latitude. That's been around only for about 400 or 500 years. And that gives you a unique position on the sphere. That's called the horizontal datum, which is the model of the Earth and the longitude and latitude definition. In Australia, that's GDA 2020. So in civil projects, we're talking about long civil projects, we don't use longitude and latitude. We use a thing called a map projection and map coordinates. And for what that is you basically have something like a cylinder in this case. You go from the center of the Earth through the point on the surface of the ellipsoid, and you hit this cylinder. You roll that out, and that'll give you what we call eastings and northings, or map coordinates. You can't have something like that for the whole of the Earth, so usually it's broken up into smaller zones. And the universal transverse Mercator is the one used virtually around the world, which breaks it up into 6-degree zones. And so in Australia, we're using that. That's what our MGA 2020 is. It's a UTM. And basically, we go from zones 50 to 56. And the coordinates for a map projection are usually easting and northings. So for georeferencing, you require a model of the Earth and longitude and latitude, which is the horizontal datum. You need a vertical datum. I'll say no more about that, but it's an Australian height datum here in Australia. It's not ellipsoid heights at all. A map projection and a zone number. And with that, you get unique eastings and northings. And basically the whole thing is you've got a unique longitude and latitude, and you can go backwards and forwards uniquely from that to eastings and northings. So you have a model, again, coordinate system for the Earth. So for this particular project, it's say it uses MGA 2020 and Australian height datum. So basically it's telling you exactly what map coordinates you can use for the project. So in IFC 4x3, there's a thing called IFC projected CRS, which was added actually in IFC 4, and it gives you a horizontal datum, vertical datum, map projection and zone number, all that stuff I mentioned. It was missing, you have to have another thing to go with it, and for IFC 4 it was missing what we needed. And that was added into IFC 4x3 called a rigid operation. It's just a translation in X, Y, and Z. So basically in your file, you'd have a horizontal IFC projected CRS, which will say it's GDA 2020, Australian height datum, MGA 2020, zone 56, and a null 000 translation. That's what you just have to put in your file. And what that tells you, if that's in your file, when you're reading in your IFC file, your data is going to come in map coordinates of eastings, northings, and Australian height datum in the map projection that was given in that file. So where I'm sitting here is my coordinates are those eastings and northings, which is a 9 and 10 digit number. That is what you'll have in your IFC file. And basically 00 is totally banished. You don't use that at all in georeferencing. So that's what we've been waiting for about the last decade, is to actually be able to use our proper map coordinates in the file. What about local engineering coordinates? Basically, that's just like building and people that, no problem at all. That's very easy. The building designer in local engineering coordinates just has to figure out when the data is being read in, how it comes into map coordinates. Simple as that. But for us civils people, it's fantastic. We're now off the hook. All our work is done in map coordinates, it's up to the vertical BIM people to figure out how they get their data across to us. And how is this done? Basically, luckily, locally things are flat. And so we can use that idea is that when you're in a site that's very small, you can actually work out a clockwise rotation in the X and Y plane, a factor applied to both X and Y, and a 2D translation, and that'll take you from your local engineering coordinates to map coordinates. And the reverse will go the other way. And this particular one is known as a 2D helmet transformation. So basically, it's just a fairly simple equation. So this allows you to go backwards and forwards. So how do you get that information? Well, again, if the site is small, what you can have, if you've got a number of points with both coordinate systems, you can do least squared analysis to give you those parameters that you need. So usually someone like a surveyor can tell you that quite quickly. But also, if you're going to assume that that factor is 1, then it can be simplified. What it tells you, it's a counterclockwise rotation between your local north and the map grid north. That's the north from the map coordinates, not true north or anything like that. And then for your 0, 0, you just need to know the eastings and northings from that point. And hey presto, you can go these equations to go between the two systems. So it's fairly easy. You can have a slightly more complicated one, or you can assume the factor is 1. We can talk about that later, about what could be wrong with assuming the factors are 1. Right, so in IFC 4x3, they've added in this IFC map conversion scale with all these parameters. And basically what it means is you can use those to give you a counterclockwise angle theta. And in matrix form, that's the equations that it produces on your data as it's read in. And basically that's part of that is the helmet transformation. There is a scale in there, but basically that's going between units. So again, we're going to work totally in meters. That would actually be 1. So there's now something in there. So if you've got a map conversion scale in there instead of your rigid operation, then you're saying the data in the files in local engineering coordinates, and that map conversion scale will bring it into map coordinates as we read it in. So if you've got a local engineering coordinate system, all you have to get, say, is a number of points in both coordinate systems and work out those parameters. And you whack that information, projected CRS, a map conversion scale with those parameters in your file, and hey presto. The big thing you've got to know there is those parameters only apply to one small area. If you've got a lot of different small areas, they're going to have different parameters. So a classic case is for a road or rail, where it'll be in map coordinates. You need different IFC map conversion scaled for all the little projects along the way. You can't use the one thing, you'll be totally out of it. There's one horrible truth that you all have to remember. We have what we call ground meters, is what you use with your normal ruler. But when you're using map coordinates, you have the distance between 2 points is what's called map meters. They're not the same thing. So basically, you can have local engineering coordinates, which use your ground meters and short distances, or map coordinates, which will have map meters and goes large distance. You can't have both. So you've got to be very careful in a project, you know exactly which one you've got and how you go between them. So there are 4 cases in IFC 4x3 now covers. You've got the coordinates in the file in map coordinates, so you just need IFC projected CRS and rigid operation. You've got map meters, you just need a translation to get across. That's when you've got truncated map coordinates. The third case is when you've got local engineering coordinates, and if you've got the projected CRS and map conversion scale, it'll get you the map coordinates. And there's a total flatland one, which is IFC 2x3, where everything's just in local engineering coordinates. Other things we've got there, tins, no problem. There's a triangulated irregular network, and this is where it's gone across between, say, 12D model and US BIM in projected space, no problem. There is IFC alignment, which has your normal civil, horizontal, and vertical geometry, and that's in the semantic part of the definition. That's perfect for going between civil products. And this is a 33-kilometre job that's gone between 12D model and US BIM. This was a test case for IFC 4x3. The final thing is strings. And there's a thing in there called IFC annotation. It has a point, polyline, and polygon. So strings can be represented in IFC. And even for AS5488 for underground utilities, where you need attributes on vertices and segments, that can be all covered by rel nesting these IFC annotations. So when you've got a survey string with all that data there, it's got georeferencing, you can see string names go across, the models can go across backwards and forwards. You've got your attributes for the string, you've got your attributes for your vertices, and you've got your attributes for your segments. All go backwards and forwards. So all your survey data and any string data does work. It's all there in IFC. So for civil, you have your general georeferencing, large coordinates, all the things you need for strings, names, alignments, tins, and you can actually have models as well. So for you guys in civils and surveyors, you can finally rejoice. The world's no longer flat. Horizontal BIM is finally on an equal footing with vertical BIM. Thank you.